Good morning, my name is Natalia, and today I'll be demonstrating the behavior of my counter, which operates as a clock. This means the digits will go from 0 hours and 0 minutes to 23 hours and 59 minutes. Going up to down on the displays, the upper display belongs to the least significant bit, whereas the lower one belongs to the most significant bit. Therefore, these two bits will show the minutes and these other two the hours. Each digit has an inner asynchronous ascending counter that will reset once the limited number or value is reached. Important note is that each counter is based on an arrangement of 4 flip-flops each. For all of them to start in 0, there's this little circuit of 3 gates. And explaining how it works, there's this AND gate that has one input coming from the signal of the clock. The other input comes from this arrangement of NAND gates and will always have an output of 1. So in the first pulse, this will be 0, and therefore the output of the AND will be 0. This 0 is sent to the clears of each flip-flop, giving automatically a signal of 0 to them and starting in 0. Now explaining the counters, starting with the first one, it's important to note that the only output that I'll be using is the Q. Also, this voltage source will power the flip-flops, and there's also one voltage source for each flip-flop that is connected to the J and K inputs and giving a signal of 1. Now, the most significant bit for this counter will be given by the output of the last flip-flop, and the least significant bit comes from the output of the first flip-flop. Regarding the clock, the first flip-flop is connected directly to the signal of the function generator. This function generator is giving a signal of a square waveform with 160 kHz and a peak voltage of 2.5 volts. Now, the output signal of the first flip-flop will go to the clock of the second flip-flop and so on until it reaches the last. Now, this digit needs to go from 0 to 9 and then reset. So there's a mod 10 that needs to be done. What I decided to do is locate the 1s on the binary number. So for the 10, its binary number is 1010. Going from most significant bit to the least significant bit, the 1s will be located on the output signal of the last flip-flop and the output signal of the second flip-flop. That's why this NAND gate is connected to one. It has its inputs connected to these signals. When these conditions are true, the output of this NAND gate will be 0, and this signal is sent to the clears of each flip-flop, resetting the counter. In any other case, the signal will be 1, the output signal will be 1, and will have no effect whatsoever in the counter. Now, regarding the 7-segment display, this gate has its inputs connected to the outputs of each flip-flop. So the A input is connected to the Q output of the first flip-flop. The B input is connected to the second flip-flop, the C input to the third, and the D to the fourth. The 3 remaining inputs are connected to this digital signal of 1, and each output is connected to its corresponding input in the 7-segment display. This arrangement is the same in every counter. Going to the second counter, the first clock comes. The signal for the first clock comes from the output of the last counter. And the arrangement is the same. The output signal of the first flip-flop goes to the clock of the second and so on. But in this case, the digits go from 0 to 6. or from 0 to 5. So there's a mod 6 that needs to be done, and its binary number is 0, 1, 1, 0. So the ones will be located in the output signals of the flip-flops in between. This is why the NAND gate has its inputs connected to the output signal of the second flip-flop and the third flip-flop. When this is true, again, the signal will be 0, the output signal, and this 0 will be sent to the clears and reset the counter. Now for the third counter, just focusing on the mod 10 that needs to be done, because this digit needs to go from 0 to 9. It's the same as the first one. This NAND gate is connected to the output signal of the second flip-flop and the last flip-flop, because the binary number for 10 again is 1010. When this is true, the output signal will be 0. But then there's an arrangement that needs to be done for when the 24 is reached, but I'll talk about that in a bit. Now going to the fourth counter, this digit only needs to go from 0 to 2, so a mod 3 needs to be done. The binary number for 3 is 0011, so this NAND has its inputs connected to the output signal of the first flip-flop and the second flip-flop. Now, for the mod 24 that needs to be done, because once the 24th hour is reached, it needs to reset again and start in 0. So what I did is locate the 4 and the 2 that makes the 24 hour in these counters. So the 4 in the 24 will come from the third counter. Its binary number is 0100. So in this case, there's this NAND gate, and one of its inputs comes from the output signal of the third flip-flop in the third counter, meaning that if this output is 1, it means that the number could be 4, and the signal goes into this gate. Now, the 2 in the 24 comes from the fourth counter, and the binary number for 2 is 0010. So the 1 is located, or could be located, in the output signal of the second flip-flop in the fourth counter. So that's why the other input of this NAND is connected to this signal. If this is true, the number, then it's 24. And the signal, the output signal, goes to these AND gates that has its other input being the output signal of the NAND gates of the previous mods that I talked about, being for the third counter the mod 10 and for the fourth counter the mod 3. If only one of these conditions is true, then the output signal of the AND would be 0, resetting the counters. If none of them are true, then the signal will be 1 and will have no effect. Now I'll attach a video in fast motion of how the counter works. Thank you so much for your attention and also for watching.